Thank you, Peter. Well, I hope you can hear me, so great to be here. I think it's a great initiative that the machine learning summer school comes to Eastern Europe. Well, I can consider, at least to some extent, myself as part of being Eastern European. So it's interesting that Peter mentioned the NeurIPS in LA in 2017, so that's, I think I've been a little bit longer around, so I still remember NeurIPS being a few hundred people. But that was, I think, the first time when I came to realize, exactly as Peter mentioned, that this has become a huge and very impactful community. So we gave there actually, not the first, but the first tutorial on geometric deep learning with Jean Bruna, with Arthur Schlam and Xavier Bresson. And we had an audience of more than 3,000 people for the tutorial. So it looked like a stadium. I could hear myself with an echo, so it was really a really dramatic experience, and yeah, of course, all the industrial parties. So it was totally crazy. And I remember also some people asking weird questions like whether AI has soul, and I didn't even know what to answer to this. I thought that, well, probably maybe people coming from intersection of computer science and philosophy. But then I read in newspapers that actually in LA people were excited about AI conference coming to their town, so just random normal people bought the tickets to get them to see what it is about. So apparently I bumped into one of these people. So I would like to talk today about geometric deep learning. So maybe a disclaimer, as Peter mentioned, I'm the DeepMind professor of AI at Oxford, but actually I'm not an employee of DeepMind, but I have probably this is a unique position. It allows me to harass DeepMind, or now Google, at every EEML conference, asking to give me my chair. So far they have had only stools, which is obviously not the same thing. But I think we had to reciprocate. So last month when Demis got to Oxford to get his honorary PhD, which we awarded him, we made him sit in a very uncomfortable chair for almost an hour. So according to his admission, it was one of the most uncomfortable, probably a very historic chair where some prime ministers have sat in the past. So anyway, I would like to start with a little bit of historic introduction and why geometry actually has anything to do with machine learning. And I would like to convince you that this concept of symmetry, about which Hermann Weyl, that I quote here, wrote very poetically, is really a fundamental idea, not only in mathematics, I think, in art, in other branches of science. So this is, as we'll see, very foundational to the very universe in which we live. And the term itself comes from Greek, and ancient Greeks believed that symmetry is a very important thing. So it's really foundational to the very world we are living in. Plato, for example, considered what nowadays we call the Platonic solids, symmetric polyhedra, to be so important that, according to him, all the stuff around us is built out of these tiny symmetric shapes. And it's not such a crazy idea if you think of crystallography, so that's exactly how crystals work. And also, according to a legend, he had an inscription at the entrance to his academy saying that no one ignorant of geometry should be allowed to enter. Actually, we have in Oxford, at the entrance to the Department of Mathematics, it's somewhere hidden on the floor in Greek. And Greeks are also credited with, if not inventing, at least formalizing geometry that we still teach as the geometry at school, which is Euclidean geometry. That, as you know, is based on 5 axioms or postulates from which all the theorems are derived. And as you also probably know, there was this 5th postulate of Euclid about parallel lines that stood out somehow, and for many hundreds of years, probably even more than that, a line of illustrious mathematicians tried to prove it, to see whether you can actually derive it from other axioms, to no avail until the beginning of the 19th century, where finally came the realization that you can actually construct other self-consistent geometries without resorting to the Euclidean postulate about parallel lines. So Gauss presumably was one of the first to entertain these ideas, though he never published. And then the 2 concurrent works by Nikolai Lobachevsky and Janos Bolyai who are credited with the first publication of the non-Euclidean geometry. So basically what it created in geometry towards the second half of the 19th century, this unhealthy situation when there was a zoo of different types of geometries that people didn't really understand how they are related to each other and what actually defines in geometry, and it required a radical paradigm shift which came in 1872 from a young German mathematician. He was only 23 years old when he got appointment as a full professor at the University of Erlangen in Germany. So his name was Felix Klein, and he introduced what you can call second algebraization of geometry, basically suggesting to think of geometry as a space with some attached group of transformations. So basically studying what happens to a geometric shape when you subject it to transformations by actions of some group. And the classical Euclidean geometry can be derived from rigid motions, rotations, reflections, and translations. And you can also consider bigger groups such as affine or projective group. And in fact, he also used projective group to create the first model of hyperbolic geometry together with Eugenio Beltrami. He was actually very skeptical at first about non-Euclidean geometry, but then he changed his mind. So this was very transformational in mathematics. In geometry, it also, in some abstracted form, created new branches of mathematics. One of them was category theory. But in physics, it allowed basically to come to the realization that the very basic laws of the universe can be derived from first principles of symmetry, same way as Klein did it in geometry. And probably the most famous result is by Emmy Noether, who showed that in certain physical systems you can derive conservation laws that until so far were empirical from basic considerations of symmetry. So, for example, the conservation of energy could be derived from symmetry of time. And this idea, through the introduction of what is called gauge symmetry by Weil, and its evolution by Young and Mills, resulted in what nowadays we call the standard model. So all physics that we now know and can explain actually can be derived entirely from these considerations. So physicists like to distinguish between what they call external symmetries. So this is the Poincaré group that gives rise to the Minkowski geometry of special relativity, and the internal symmetries of quantum fields that give rise to different forces or different interactions between particles. And I think it was laconically and beautifully summarized by Philip Anderson, Nobel laureate in physics, that it's only slightly overstating to say that physics is the study of symmetry. Now, what does it have to do with deep learning? In deep learning, we also have this zoo of different architectures that historically were derived for different problems, for different types of data, in different contexts, like convolutional neural networks that originated actually from work in neuroscience and were devised for early problems of pattern recognition in images, or recurrent neural networks that originated for the study of time sequences, and graph neural networks actually have their origins in chemistry. So in this zoo, we lack a common denominator, and this is what we try to do with geometric deep learning. So it's an umbrella term for basically providing geometric explanations from, again, similar to Klein's Erlangen program, from first principles of symmetry. And Petra mentioned the book that we are hopefully going to finish this year. So we actually have a lot of material online that shows in more details what exactly we mean here. So let me start with, maybe as a motivation, with a simple setting of a machine learning problem, right? So everybody heard about cats and dogs, right? So that's somehow is given as a trivial example. It actually comes from David Mumford, Fields medalist who was interested in pattern recognition, when some DARPA representative was asking him when we will get some sophisticated reasoning. He said that we're at the stage where we can barely distinguish between cats and dogs, and somehow it became a meme, and this is how we always give this example. So if we want to create a cat and dog classifier, you can think of cats and dogs, right? So these images, some high-dimensional vectors, right? And you can just parse them into these vectors and feed them into some black box that produces, let's say, 1 and 0, depending whether you want it to be a cat and a dog. So the black box, historically, since the late 50s, contained neural networks, right? So we know that these are universal approximators. A two-layer perceptron can approximate to any desired accuracy any continuous function, right? So in a sense, they can represent anything you want. So this is actually not a single result, it's a class of results, the universal approximation theorems. So they're kind of existence results, right? So they tell you that it's possible, but they don't tell you how. In particular, they don't tell you what should be the number of training examples, right? The samples of the function, and what should be the number of neurons, how to find the weights, and so on. And of course, continuous functions are probably too broad a class, right? So there can be infinitely many continuous functions that pass through some set of points. So we need to restrict our class, and we need to introduce some form of regularity. And people studying approximation of functions, right? Mathematicians have useful notions of regularity, such as Sobolev spaces or Lipschitz continuity, right? And unfortunately, this doesn't work well in machine learning problems that need to operate in high dimensions. And if you take very well-behaved mathematical class of functions, such as Lipschitz continuous functions, and you try to scale the number of dimensions, right? So if instead of considering two-dimensional functions, what about three-dimensional functions, or more generally d-dimensional functions, we will see that the number of samples that we'll need to take will be exponential in the number of dimensions, right? So if I have some fixed error epsilon, then the number of samples will increase exponentially with d. And of course, it makes these approaches impractical, right? So we simply will probably run into the problem that the number of samples that I need to show to my neural network will be more than the number of particles in the universe. And this is a class of phenomena that colloquially are known as the curse of dimensionality. So this is also an ancient term that goes back to Bellman from the 50s. And we need something new. We need some different kind of regularity that we want to assume about our functions. And this is where the basic foundation of geometric deep learning comes. We call these geometric priors. And instead of considering our images in our example of cats and dogs as just d-dimensional vectors, we would like to consider them as signals that live on some low-dimensional domain. So basically, images, you can think of them as functions, right, or signals that live on a grid or in a plane. And on this grid, we can apply some group of transformations. So for example, these can be translations that would act on the signals through what is called the group representation, right? So in this example, I have the translation group that operates on points in the grid, and this representation will be the standard shift operator that operates on images that are defined on the grid. And now we have functions, right? In our example, that was the cat and dog classifier, so function f, that takes as inputs these signals, and we want to understand how it interacts with the action of the group, right? And one example could be invariance. So no matter how I translate my input, I want the output to be the same. This is very useful when I want to detect patterns in images. I don't care where the cat is located in the image, as long as it is a cat somewhere, I want to say that this is a cat, right? So we call these functions invariant, right? And another type of invariance, which is more general, actually, it's you can obtain invariance as a special case of it, is a property that we call equivariance. So in this case, the structure of the input is the same as the structure of the output, and there is a commutativity property, right? So if I translate my input, the output should be translated in the same way. So early geometric architectures actually came from the field of neuroscience, maybe without explicitly admitting it. So the classical work of Rubel and Wiesel, a duo of neuroscientists from Harvard that got the Nobel Prize for the study of the organization and the function of the visual cortex, what they showed is that the cells in our brain in the visual cortex have local connectivity. And this gave inspiration to a new class of neural networks initially developed by Kunihiko Fukushima in Japan in the early 80s, which he called the neocognitron. And these were neural networks where he exploited the same structure. Basically, he had special types of cells that are locally connected into what neuroscientists call receptive fields. And this idea was not very practically implemented on computers of that time. So the breakthrough came from Yann LeCun, who was the first to simplify this into linear operations that are called convolutions. He actually didn't call them by this name in the initial paper that appeared in '89. And he implemented it on one of the first digital signal processors. So at that time, he was working at AT&T or Bell Labs, which was actually manufacturing these chips. And it allowed to do complicated at that time, still probably by standards of today, pattern recognition systems in real time. So that was the first practical use of these architectures. And if you look at the essence, what was the new thing that convolutional neural networks brought? It was this local connectivity and shared parameters, right? So by local connectivity means that not every output neuron is connected to every input neuron. It is connected only to its receptive field. And then the shared parameters means that the function that I implement at every position is the same. It's just the input that looks differently. And this actually was the happy marriage with DSPs and later with GPUs, because these processors know to do one thing very fast, right? So it's called single instruction multiple data. So they can multiply an input vector by some parameters and sum everything up, right? So multiply, accumulate, that's the kind of instruction that is done efficiently. If you look at it from algebraic perspective, right? So the weight matrix in a convolutional layer looks like this. So the shared parameters give it this special multi-diagonal structure. We call these toplets or circumvent matrices, and this is actually the convolution operation. So you can think of convolution axiomatically. It arises as the only linear operation that commutes with the translation group. So you can derive convolution from first principles, and this makes it a special instance of our geometric deep learning blueprint, right? So you can choose your domain to be the grid, your group to be the translation, then the signals that live on the grid are images on which the group acts through the shift operator, and then convolution is a translation equivariant operation, actually the only linear translation equivariant operation that you can define. Now, in recent years, we need to deal with different type of data, and here's an example. So this is data that looks like a graph. Good example comes from chemistry, right? So we can represent molecules as graphs. The nodes are atoms and the edges are chemical bonds. And this is our favorite molecule of caffeine that we all like drinking in the morning to keep us productive. And one of the typical tasks that we try to do, for example, when we are developing new drugs, is predicting some physical and chemical properties of these structures, right? So I want, for example, to predict whether a molecule is toxic, right, or whether it's soluble in water, right? So important properties that we want to test when we do virtual screening. So the problem here is that we don't really have a canonical way of parsing the graph into a vector, right? So I can order the nodes of the graph in a totally arbitrary way, right? So any permutation would work. So basically what we need to incorporate by design into any learning architecture that will take as input these kind of structures is this ability to say that the output wouldn't change when we permute the input, right? So in other words, in this example, the properties of a molecule do not change when we just order the atoms, because this is our convention, right? So the molecule doesn't have any order of atoms. So graph neural networks, about which we'll be talking in a few minutes, also implement this idea of locality and shared parameters, basically by doing what is called message passing. We have a permutation equivariant layer, right? So if I permute the input, the output is permuted in the same way. And when we want to predict a single property of the graph, we have a permutation invariant readout, right? And again, this is a special setting of our geometric deep learning blueprint. In this case, the domain is a graph. The signal are node features, and the permutation group on the nodes of the graph acts through the permutation matrix, and message passing, about which we'll be talking in a second, is a permutation equivariant function, okay? And if we want to, again, to make this analogy to physics, remember we had this difference between the external and internal symmetries. So the external symmetries are analogous to these domain symmetries. Internal symmetries are analogous to the symmetries of the data. And again, molecules are a good example. So in molecules, the atoms might not only have the atom type features, like whether it's carbon or oxygen, but they also have geometric coordinates, right? So these are graphs that live in three-dimensional space. So if I, for example, take my molecule and rotate it or translate it, I don't want the molecular properties to change, right? So again, how the molecule is positioned in space doesn't really matter. So we want what is called SO3 invariance. So SO stands for the special orthogonal group. This includes orientation-preserving rigid motions. So importantly, we exclude reflections because they do change the chirality of the molecule and change the chemical properties. But this is a special type of graph neural networks that are called equivariant, maybe a little bit tautologically, or geometric GNNs. And here we have two types of symmetries. We have the symmetry of the domain, right? So the permutation of the nodes of the graph, but also symmetries of the data. So the rotations and translations of the coordinates that are some of the features attached to the nodes. And we have a special type of geometric message passing that accounts for both of these symmetries. And this was very important in AlphaFold 2, the famous program from DeepMind that predicted the 3D structures of proteins. And these architectures are now ubiquitous in chemistry and drug design. You can, same way as you can generate images nowadays, you can have generative geometric architectures that can generate new molecules that will bind to some target protein, or even generate new proteins with desired properties that can, in their own turn, used as biological drugs. So again, geometric deep learning is a very general principle. You can apply it to grids with the translation group and get CNNs. You can apply it to graphs with the permutation group and get GNNs, or some more exotic architectures like looking at the local symmetries, what is called the structure group of the manifold, when you work with meshes and surfaces. And more or less any architecture that you have heard about, whether it's transformers, whether it's CNNs, whether it's LSTMs, can be derived from these first principles of symmetry. So in a sense, it's a kind of one-size-fits-all class of architectures. And from the reaction, I understand you might have seen this little video. So let me talk about graphs. I think I don't need to convince you that graphs are really ubiquitously used in mathematics as models of systems of relations and interactions. You can use them at all scales, from very small scales like molecules to very large scales such as social networks. And basically when we talk about graphs, so here we'll be talking about undirected graphs, right? So these are, the graphs have n nodes that we index just by numbers, and undirected edges are unordered pairs of these nodes, and we assume that we have d-dimensional features that are attached to every node. So one thing that when we represent these structures on the computer, we need to account for the fact that we don't have canonical ordering of the nodes, right? So if I reorder my nodes, I need to reorder these, the representation of the graph in the form of the adjacency matrix and the feature matrix, which will be of size n by d. Right, so we have n factorial such permutations. So it's impossible to learn all of these, so we must design architecture that accounts for it automatically by construction, right? So this is a very large group. So the typical tasks that we encounter in graph learning are graph level tasks, such as predicting chemical properties of a molecule, or node-wise tasks where we, for example, want to detect spammers on a social network. And in the first case, we want a function that outputs the same number if we change if we apply permutation to the input. In other words, it's permutation invariant function. In the second example, the output is the same, it has the same structure as the input. So we want the function to be permuted in the same way if we permute the input, right? So we call these functions permutation equivariant. And graph neural networks are essentially parametric graph functions, so they take as input the graph with its features, apply something to it, and produce some output. And this something usually has the form of message passing, so every node in the graph looks at its neighbors, and each neighbor sends a message to the node to update it, and then the messages are aggregated. So because, again, we don't have canonical ordering of the nodes, the aggregation must be a symmetric or permutation invariant function such as a sum. Now, this is the most generic form of message passing. We can also consider special cases. The case where aggregation is done by through the attention mechanism, right? So we sum up the neighbor node features with coefficients that depend on these features. So the most probably commonly used and most famous architecture in this class is the graph attention network. I think it was one of the first publications of Peter when he spent his time at Mila. And even further simplification, we have just linear aggregation of the node features with coefficients that depend only on the structure of the graph. So this is called convolutional type architectures, and they actually boil down to the classical convolutions on grids. And if I write it in matrix vector notation, I can write convolutional architectures like this. So I have a matrix A that captures the structure of the graph, right? Adjacency matrix or some version of it, multiplying the feature matrix from the left. Attentional architectures, you can still write them in this way, but now A is not a fixed matrix, it's a matrix valued function. And general message passing is some nonlinear operator. Now, first thing that you probably want to ask is actually how generic these kind of message passing architectures are, right? So in other words, what kind of functions can we compute with this procedure? And for this purpose, we want to study the expressive power of graph neural networks, and it appears that under some technical conditions, the class of functions that are universally approximating permutation invariant functions on graphs, if and only if it can discriminate graph isomorphisms, right? So what I mean by graph isomorphism is being able to tell whether two graphs are structurally equivalent, right? If I have edge preserving bijection between the nodes. So in other words, universal approximation, again with some mild technical assumptions, is equivalent to graph isomorphism testing. So if you wonder why everybody is obsessed with graph isomorphism testing, it's exactly because of this reason, right? So it's the analogy of the universal approximation results that we've seen before, right? So what it means ideally is that basically we want to, by design, right, isomorphic graphs will have identical representations, right? So GNNs are unable to distinguish between them. So all these examples shown here are examples of isomorphic graphs. That should be mapped by MPNNs to identical representation. The converse, unfortunately, is not necessarily true. So there might be indistinguishable non-isomorphic graphs, right? So there might be two different graphs, non-isomorphic, that our message passing architecture will map to the same representation. So, and the extent to which this happens, we would like to try to analyze. And for this purpose, we would like to use an antique paper that was actually inspired by problems in organic chemistry. So that's the famous work of Andrei Lehmann and Boris Weisfeiler, two Soviet mathematicians that works with a Romanian organic chemist called Georg Vladuț, who tried to determine whether structurally compounds are similar and search them in very large databases. So basically what they devised was what initially was thought to be a polynomial time test for whether two graphs are isomorphic. It's actually known that it is not exponential time. So it's not an NP-hard problem, but it's also, we don't know of any polynomial algorithm for graph isomorphism testing, so now it's put somewhere in intermediate complexity. And what it does iterative color refinement. So we start with a graph where every node is colored in the same way, and we examine the structure of the neighborhood of every node in this graph. So here we initially have two types of neighborhoods, right? We have a node with two neighbors and 3 neighbors. If we apply an injective function, something like hash function, these will become two distinct new colors, and we can call them, let's say, yellow and green. And now we have a graph with refined colors, so we can repeat this procedure again. Now we have 3 types of neighborhoods. These will become 3 new colors, and we proceed until the colors stop changing. So at this point, we produce a histogram of colors. And by the construction of the algorithm, if I give you a different graph, and the colors are different, the distribution of colors is different, I can guarantee that the graphs are non-isomorphic. But if the distributions are the same, we actually don't know. So in other words, it's a necessary but insufficient condition for graph isomorphism, and you can come up with simple examples of graphs that cannot be distinguished by this Weisfeiler-Lehmann procedure, but they are not isomorphic, and examples include all graphs that have connected patterns with more than 3 nodes, like triangles, cycles, and so on. Which is actually, ironically, given that this algorithm arose from organic chemistry, in organic chemistry we have a lot of these patterns in molecules, right? So we need to do something more. So if you look at the expressive power of message passing neural networks, right? So ideally we want to look at all permutation invariant functions, right? Or equivalently all graph isomorphism discriminating functions. This is what we can distinguish by WL, right? What the subset of functions that can be computed by WL. We know for sure that there are functions like counting the number of cycles that cannot be computed by WL. And MPNNs, because of the structure of the algorithm, right, of message passing, sit somewhere here, right? So, and the question is, can we actually push the boundaries of MPNNs? Basically, what should be the choice of the message passing architecture in order to make it at least as powerful as WL test? And the result from about 5 or 6 years ago is that under some technical conditions, we can upper bound the expressive power of message passing by that of the Weisfeiler-Lehmann. In particular, if we use injective aggregator and message passing functions, it is equivalent to WL. And this gives us basically a theoretical framework to talk about the expressive power of graph neural networks, right, using this graph isomorphism formalism. But that's the rub. in practice, we know that some non-isomorphic graphs cannot be tested by WL, and even worse, in practice, some graphs might be unfriendly for message passing, right? So if I want to send information from this blob to this blob, in this example, it will need to pass through just one edge, and information might get lost on the way from one part of the graph to another. So the solution to the first problem is to use more expressive isomorphism tests. So there is an entire hierarchy of strictly more powerful KWL tests, and people have designed different graph neural architectures that are equivalent to KWL tests. In particular, the work of Hagai Maron explored it. We can also do some smart things. So you can do, for example, what we call subgraph union networks. So we consider a collection of subgraphs extracted from the graph, and you do some kind of coordinated message passing on them. So they're strictly more powerful than 2WL and strictly less powerful than 3WL. And you can also work outside of the WL hierarchy with different type of structural encoding, such as graph subtraction network, or our recent ICML paper on graph homomorphism basis. So the second problem, the practical one of the failure of message passing to propagate information is solved by what is called graph rewiring. So you decouple the input graph from the computational graph, and of course it facilitates the flow of information, but it can break the link between the practice and the theory, right? Because the classical approach to GNNs, right, that also relies on the formal analogy to Weisfeld-Lehmann graph isomorphism tests, requires us to propagate information on the input graph. So we can augment the input graph with some other structures. We can use some form of positional encoding, right? And this is very common in transformers, which are a special type of graph neural networks. You can also lift the graph to high-dimensional topological spaces, like cellular or simplicial complexes. You can, what I already mentioned, use a collection of subgraphs. You can account for the symmetries of the data. And in some special cases, like grids, you can make more specific message passing that boils down to being classical convolution. So the common denominator of all these approaches is more structure. You can also opt for choosing to ignore the graph altogether, right? So you can say that I ignore the edges and I end up with just a set of nodes. And these are some of the probably most primitive learning architectures on sets called deep sets or point nets. So they also inherit the permutation invariance that we have in graphs. The other extreme is to say that you allow to any pair of nodes to communicate. So we have a fully connected graph, right? So we completely ignore the input graph. We make a fully connected or complete graph. And this is how transformers operate, right? So in this case, the effective structure of the graph is learned through the attention mechanism for the downstream task, right? And transformers actually typically used with positional encoding because the transformer itself, right, so the message passing on the complete graph is permutation equivariant, right? I think we heard it in the lecture yesterday. So the only thing that breaks the permutation invariance, it is actually very important in NLP applications because the functions that we are interested in, they are not permutation invariant, right? The order of words in a sentence does matter, is exactly the positional encoding, right? So graph rewiring sits somewhere in the middle, and basically graph rewiring is a modern take on GNNs. You don't propagate information on the input graph, you propagate information on another graph that is somehow better or friendlier for information flow, right? Now, if we look at different objects that we can use in this bigger framework of geometric deep learning, right, whether it's grids, meshes, or graphs, so you can say that, well, they're roughly the same thing, right? So grids are special types of graphs, and meshes are graphs on steroids, right? So these are simplicial complexes where we also have high-dimensional, not only zero-dimensional nodes, but not only one-dimensional edges, but also two-dimensional triangles. So if we look at the way that we aggregate information on a grid, for example, we do have canonical order of the neighbors, right? So I can designate, for example, the top neighbor or the right neighbor, so there is no ambiguity whatsoever, right? So the group in this case would be just contain a trivial identity element. In the case of a mesh, I can designate the first neighbor and then order all the rest of the neighbors in, for example, clockwise orientation. So these are discrete manifolds. So we have the meaningful notion of orientation, but the choice of the first neighbor is ambiguous, so everything is defined up to rotation. So in differential geometry, we call it the structure group of the manifold. This is typically SO2. In case of graphs, as we've seen, everything is defined up to arbitrary permutation. So in a sense, graphs have the least structure, right, or the biggest ambiguity. Another thing is when we look at grids and meshes, we can think of them as discretization of some continuous objects, right? So a grid is discretization of the plane, a mesh is discretization of a manifold or a two-dimensional surface. We don't have immediate continuous analogy like this for graphs, right? So it would be nice actually to try to devise graph neural networks from some continuous problems. And this is what we like to call physics-inspired GNNs, where we can think of a physical dynamic system. So now the metaphor I would like you to have in your mind is to think of a node as of a graph as a particle in some d-dimensional feature space that undergoes some evolution, right? So it follows some trajectory that is shown here in this red line. So basically our feature matrix is now a function of t, right? I remind you that its dimension is n by d, n is the number of nodes, t is the dimensionality of the features. And how these trajectories are computed, basically what governs the evolution of this system is a set of differential equations that are right here. So if we discretize it at, let's say, fixed time steps, every time step will correspond to a layer, right? And the graph acts as a coupling function, right? So the particles interact with each other. How do they interact? They interact along the edges of the graph. And we'll see that in some settings we can also think of the graph as a discretization of some continuous object. Now, we can put a lot of different things here as the differential equation, but probably the first thing that comes to your mind when you think of propagation of information is a diffusion process, right? And diffusion equations were, or in particular heat diffusion, was probably one of the earliest mathematically described physical phenomena by none less than Isaac Newton himself. So in a famous paper published anonymously in the Transactions of the Royal Society in 1701, he described a homemade thermometer and physical experiments. So he was heating objects in an oven and letting them cool, and he measured the temperature at fixed time steps and devised a mathematical law that nowadays we call the Newton law of cooling, that tells us that the temperature a hot body loses in a given time is proportional to the temperature difference between the object and the environment. So this is a very, very basic mathematical principle that you can apply to other types of diffusion, chemical diffusion, or even abstract diffusion like propagation of rumors or misinformation on a social network. And this is how it will look on the graph. So this is kind of local differential version of the Newton law of cooling. So what we see here, what I denote by x, right, our feature at the node, think of it as temperature. So the self-temperature is the feature of the node itself. The temperature of the environment is the average of my neighbors, and the rate of temperature change is the temporal derivative, right? So if I rearrange the right-hand side, let me write it like this. What I see in parentheses is the graph analogy of the classical gradient operator, right? So what it does, it takes signals that live on the nodes of the graph and computes the difference between the endpoints of an edge, and now I get a signal that lives on the edges of the graph, right? So a little bit similar to scalar and vector fields from classical calculus. Now, what is written here is the opposite, right? Or technically what is called the adjoint operator, the divergence. So it takes a vector field, right? Or a field or a signal that lives on the edges of the graph, sums all the information on the edges that share a node, right? And gives us a signal that again lives on the nodes of the graph. So together the divergence of the gradient or minus divergence of the gradient, depending on the notation, is called the Laplacian operator. And this is the basic, simplest version of a diffusion equation on a graph. So the Laplacian here, you can write it as a matrix. It's a sparse matrix, has the same structure as the adjacency of the graph. And basically what it tells you is what is your difference from your environment, right? And also heat equation is a prototypical example of what is called the gradient flow. So this is a term from calculus of radiations. If you're not familiar with it, think of steepest descent. So it's a type of evolution equation where we go in the direction of negative gradient of some energy. And for heat equation, we know how this energy looks like. We call this the Dirichlet energy. What it does, it looks at the sum of the squared norms of the gradient, right? So it's kind of smoothness of the node features, right? So if I'm different, very different from my neighbors, then the energy will be high. If I'm similar to my neighbors, the energy will be low. And it decreases along the heat equation, and in the limit, all the energy will become constant, right? So in graph neural networks, we call this over-smoothing. And what it does is something like this, right? So again, if you have this mental picture, all the nodes in the feature space will collapse into a single point. at some time, right, in the limit. And this is something that is typically considered undesired, but if I know that my graph is homophilic, in other words, my neighbors are similar to me, actually this idea of oversmoothing is a very good one. So we can run a diffusion equation with boundary conditions, so these will be nodes with known labels, and we can do what is called label propagation. So I propagate my labels to unlabeled nodes, and under this assumption of homophily, it works extremely well. If the graph is not homophilic, of course, we need something more sophisticated. So again, if we go back to this mental picture of a dynamic system, so the way that you can think of traditional GNNs, you start with some evolution equation, right? You discretize it, so you have a difference equation, right? Every k here corresponds to a layer. And then you parameterize these evolution equations, right? So each layer has its own set of parameters, right? The weights of the neural network. I will try to convince you that you need to do something different. So you start with an energy. You parameterize an energy. And then you derive the evolution equation as a gradient flow of this energy. Now, it already restricts quite substantially your set of possibilities because not every evolution equation is necessarily a gradient flow, right? So you start with something that has certain structure, has certain architectural constraint. What you gain in exchange is some form of interpretability. And when I say interpretability, I don't mean the usual term that attributed to it in machine learning. What I mean is that we can mathematically guarantee that certain things will happen or will not happen. And in particular, let's look at this example. So we have a graph here that is totally heterophilic, right? So the colors here represent the labels of the nodes, right? And you see that blue nodes have all red neighbors and vice versa. So the positions of the nodes represent some toy two-dimensional features. And the task here is node classification. I want to separate between the reds and the blues, right? So you see that there exists a trajectory that, of these nodes that separate them perfectly. Now the energy that we consider here is a generalization of the Dirichlet energy. So, and we have two types of interactions between the particles, right? If you think of them in terms of physical system, we have repulsive and attractive forces, and the attraction happens along the positive eigenvectors of W, and the repulsion happens along the negative eigenvectors of W, right? And you can see them here, right? So, and the evolution equation, right? So the gradient flow of this energy looks like this, and you can recognize, I hope, a convolutional type architecture, right? So why do I say that it's convolutional? Because this matrix A is fixed. It's dependent only on the structure of the graph. It's some normalized adjacency matrix. It's independent on the features, right? And typically, the folklore statement in graph neural network literature says that these type of architectures are not good for heterophilic settings, right? And the motivation that is given is that A, this matrix that averages your neighbors, acts as a low-pass filter. And if the graph is heterophilic, you have apples and oranges among your neighbors, you are averaging them together, you will get nonsense, right? So this is actually not true. And the fact is that we have also the matrix W on the right. And it's really the interaction between these two matrices. You can think of them both as filters, right? So you can think of them roughly as an analogy of two-dimensional Fourier transform. And the theorem that we can prove that this kind of linear graph diffusion, right, convolutional GNN, what we can call, if we appropriately design the channel mixing matrix, so it has to be symmetric in order for it to be a proper gradient flow. And it has to be sufficiently large negative eigenvalues, which means that we have enough repulsive forces, can provably avoid oversmoothing. As you see here, right? So we don't have a situation where everything collapses into a single point. We have what we call high frequency dominated dynamics. So we have basically this perfect separation between the node classes. So this is a contradiction to this folklore that we often see in the literature. And if we can see how it works on graphs with controlled level of heterophily, we can compare it to the toy examples where we ignore completely the structure of the graph and apply just node-wise multi-layer perceptron versus classical graph convolutional architecture from Kipf and Welling, where we don't have this structural constraint, and we can see that we perform as well as GCN in the homophilic regime and as well as the node-wise MLP in the heterophilic regime. And again, I want to stress that this is a convolutional architecture. It just we just by this new mindset we force certain architectural choices that would probably be difficult to learn from scratch. Now we can also do some more exotic things, and allow me to skip these details. But same way as we have when we think of manifolds as topological spaces where we have roughly the notion of neighbors but not notion of distance or angle, we can think of graphs in the same way. So this construction is called cellular sheaves. So we can have vector spaces attached to every node and some linear operations that take us from one vector space to another, by analogy to a fine connection on a manifold that allows to do parallel transfer. So this is what endows the manifold with geometry. So we can actually make up or learn such geometry on a graph and then run a diffusion equation, and then we can ask the questions, for example, how many node classes can we separate for different sheaf structures, right? And we have some results of this kind. So this is an alternative way of thinking of expressive power on graphs, basically by looking at the limit of the diffusion equation on this construction. So this was our work with Christian Bodner, who is, I think now he left Microsoft. So I don't know where he is now, but he was a PhD student in Cambridge. So that was an example of homogeneous diffusion, right? So the homogeneous diffusion means that the diffusivity properties of our domain are exactly the same at every point. So we can write it as a constant and take it out of the divergence operator. And if we apply it to an image, this is what it does, right? So you can actually write a closed form expression. You can write it as convolution with a Gaussian of increasing variance in time. So the kernel of this operation is fixed, and it looks like a Gaussian. And this is not desired in image processing, right? So if I want to remove noise from an image, I will be averaging it out, but I will also be destroying these discontinuities between pixels, which are important for visual perception. So what happened in the 90s, starting from the seminal work of Pietro Perona and Jitendra Malik, is to use a nonlinear type of diffusion, where we locally control the diffusion speed, and we want it to slow down or stop when we encounter a discontinuity, right? So roughly speaking, we don't want to diffuse across discontinuities. I don't want to average bright and dark pixels, right? I don't want to mix apples with oranges. And this is exactly is possible when I have the diffusivity that is inversely proportional to the norm of the gradient. This nonlinear diffusion actually is also a gradient flow of another energy that is called the total variation. And this has been extremely popular for the last 20 years. There were books and conferences and papers written on PD-based and variational image processing. It has all been wiped out by deep learning, because even though mathematically it's a very appealing idea that you can start with an energy and derive evolution equations that flow towards its minimum, it's very difficult to handcraft an energy for any type of data, and deep learning allows actually to learn the right functions from the data. So we can adapt these ideas to the setting of deep learning, and you can argue that attention does exactly this, right? So it's just a learnable version of it. So I think in the original attention paper, or in the transformers paper, they do cite all the bunch of work that have been done in signal processing in the 90s, but the lifespan of memory in machine learning is roughly the duration of a PhD. So of course now it's all forgotten. But I think if you look at it from this perspective, you will recognize the familiar concept. So we can apply this idea to graphs, right? And now we have this nonlinear diffusion. We have a learnable diffusivity function, right? That's exactly the attention that we've seen before. And if we discretize this equation in a certain way with a forward difference scheme, with certain normalization, we get the graph attention network, right? So you can derive graph attention network, right, or by extension transformers, as a special type of diffusion equations. So how am I doing with time? I think we started a bit late.
Yeah, there's at least 15, 20 minutes.
Okay, good. So remember what I promised you. So we wanted to do some continuous model for graph neural networks, but so far the thing that was continuous is time, right? So we replaced layers with continuous time variable, and we want to replace the graph, right? The graph derivatives with something that is more flexible, right? And this, remember the original motivation for it is graph rewiring, right? So we didn't want to depend on the input graph. We wanted something more flexible. So if again I look at how diffusion equations are discretized in the plane, we have many ways of discretizing the Laplacian operator, right? So these are the three different discretization of the Laplacian, and any convex combination of them would also be a valid discretization because it's a linear operator. So the point I'm trying to make here is we don't really have a canonical computational graph in classical numerical analysis, right? So we can discretize it in any way we want. Typically, we want to control the errors, right? So there are some considerations of the approximation order, but the graph is not necessarily fixed. So we want the same mindset in our diffusion equations on graphs. And here we can draw again inspiration from works that have been done in image processing. Instead of considering nonlinear diffusion, we can consider a non-Euclidean diffusion. And if you think of images, you can think of them in a slightly weird way as manifolds embedded in some high-dimensional space, right? So a color image will be a two-dimensional manifold embedded in R5, right? So the coordinates, we have a space of joint coordinates. We have the positional coordinates of the pixels, right, x, y, and we also have the color channels, right? So these are the features, R, G, and B. In total, 5 dimensions, and it's a two-dimensional manifold. And this embedding allows us to define a metric on this manifold that we call the pullback metric. And with respect to this metric, we can define a non-Euclidean analogy of the Laplacian. It's called in differential geometry the Laplace Beltrami operator. And we can define a diffusion equation with respect to this Laplacian that is called the Beltrami flow. And it appears that there is an energy that it minimizes. So it's a gradient flow of what is called the Polyakov functional. If you're familiar with high energy physics, I think it appears in the description of bosonic strings. So long story short, you can do the same thing for graphs. So every node in the graph now is equipped with a pair of coordinates. So we have positional coordinates and feature coordinates. And we have a diffusion that couples these coordinates through this, again, learnable diffusivity function that is now applied to joint coordinates. And the evolution of the x component is the standard feature diffusion. The evolution of the u component amounts to some form of graph rewiring, right? So basically, if two nodes come close in this positional space, I can decide to create an edge between them to facilitate the flow of information and the opposite. And this is how it might look like. So here we have the Cora graph, right? So it's the problem here is node classification. So it's a citation network. And there are 3 processes happening at the same time. So the color represents some projection of the features. So we are diffusing the features. The positions of the circles represent some positional coordinates. So they're also moving. And the graph is changing. So we do graph rewiring on the fly. So it's a kind of weird situation because what we are doing essentially is filtering of signal on the graph, but the graph itself is moving, is evolving at the same time, right? So it's a very disturbing picture if you think of it from the perspective of classical signal processing, but it's actually a very common thing to do in differential geometry. So differential geometers like to take a manifold and subject it to some evolution equation. So if you think of one example, these are called Ricci flows. So you take a manifold and you evolve its metric, right? So its geometric structure proportionally to the Ricci curvature tensor, right? So if I have a manifold that looks like this dumbbell, so I have 2 spheres connected by a bottleneck, so I have large positive curvature on the spheres and negative curvature on the bottleneck. And if I run this equation, actually backwards in time, this dumbbell will look like an ellipsoid, then like a sphere, and then will collapse into a point. So Ricci flows were introduced by Richard Hamilton in the 80s with the purpose of proving an important topological result that is called the Poincaré conjecture. So Poincaré conjecture that you can characterize spheres by the ability to take closed curves and collapse them into a point, right? So you can do it on a sphere always. I cannot do it, for example, on a torus, right? So if this is a closed curve and this is a torus, no matter how you evolve it, it cannot collapse into a point, right? So some other curves can be collapsed, but not this one. So, and as you probably know, Ricci flows were used by Perelman famously to prove the Poincaré conjecture, so that was a major breakthrough in mathematics. And you can ask, what does it have to do with graph neural networks? So remember this problem, the failure of message passing to propagate information on the graph. It happens in a situation when we have combination of 2 factors. So we have graphs where the number of neighbors increases exponentially. So in geometry, we call this volume growth. But also our task requires to bring information from distant nodes. So this is called long-range interactions. So when these 2 things happen at the same time, we might run into the problem of oversquashing, which we can mathematically define as some form of insensitivity, right? So if I give you a message passing neural network with L layers and certain conditions on the way that these layers operate. What I want to do is to look at the output of the neural network at the else layer at node I and perturb the input at some distant node J, right? And see how this perturbation propagates through the layers of the neural network on the graph. And we can measure basically the influence of this perturbation at the output by just taking the partial derivative of the Jacobian, right? And the norm of this Jacobian will tell us how sensitive the output is to the input, right? So if this norm is small, it means that information is somehow lost on the way to the output. And the main result of this paper by Jake Topping and Francesco Di Giovanni is that we can bound the Jacobian by some constants that depend both on the structure of the graph and the model, right? So model like number of layers, the bound on the weights, Lipschitz constant of the activation function, and topology, it comes here in the form of some power of a corrected adjacency matrix. But this is not good enough, right? So we don't really see how the structure of the graph affects the oversquashing phenomenon, and intuitively we expect that something as benign as a grid will probably be less affected by oversquashing than something pathological as a tree where the volume growth is exponential. So that's exactly where Ricci curvature comes to our help. And I remind you that in classical differential geometry on manifolds, we can think of it as what is called geodesic dispersion. So I have nearby points, and I shoot geodesics in parallel from them, and I see whether they converge, diverge, or remain parallel. So in classical Euclidean geometry from which we started, the lines are always parallel, right? So that is according to the fifth postulate of Euclidean geometry. The first example of non-Euclidean geometries that were constructed were hyperbolic geometries, so their geodesics always diverge. It means also that the sum of the angles in a triangle is smaller than 180 degrees. And on the sphere, they converge, right? So we can define something analogous for graphs. So we have now edge-wise quantity, so every edge, right, with endpoints P and Q, we can look at structures that looks like rectangles and triangles and count these combinatorial structures. So if I have many triangles of this type, then I'm locally looking at a clique. If I have rectangles, I locally look like a grid. And if my edges diverge, then I look at something that looks like a tree. So bottom line, we can capture it in a single number. We call it balance, form, and curvature. And it allows us to analyze the graph and connect it to the oversquashing phenomenon. And well, without going into too much details, we can attribute oversquashing to the presence of strong negatively curved edges in the graph. And this actually explains many graph rewiring algorithms, so I guess you will have some of these in your tutorial, but there have been many approaches trying to change the graph to make it better for the propagation of information. So some early approaches, for example, the work of Stefan Günnemann, they try to do the diffusion of the edges, right? So they use specifically a personalized page rank to embed the graph and then locally connect it. So this actually tends to connect nodes within the same community in the graph, but it doesn't create edges across communities. So it sometimes makes the problem even worse than it used to be. So it doesn't work well in the case of heterophilic graphs. So in our case, we can use something similar to Ricci flows, so we can surgically remove negatively curved edges and replace them with edges with high curvature. And Petter and his collaborators had a paper using expanders. So these are graphs that have slight negative curvature. You can think of them as really the best type of graphs that for message passing. So the graphs that they use are fixed, so you lose the permutation equivariance property. And there are multiple follow-up works that try actually to take a graph and modify it to look more like an expander. So here's the second rub, right? So the problem is that all these approaches consider just the structure of the graph. So they don't consider the task that we are trying to solve in the graph. And a good analogy from chemistry is computing different types of forces, right? So I give you a graph that represents a molecule, and I want to compute different interactions between the atoms. So in molecules, we have different types of forces. So we have what is called van der Waals interactions, so they decay very fast, right? Like 1 over r to the power 12. And we have classical colonic or electrostatic interactions that decay slowly as 1 over r, right? And the question is, if I want to compute these forces using a graph neural network, is the input graph good for the computation? So I would argue that in the first case, right, in these very fast decaying interactions, I don't really care about anything distant, right? So the graph is probably good. In the case of more distantly acting electrostatic interactions, I might need a fully connected graph, right? So something like looks like a transformer on a complete graph. So basically in this example, we have the same graph, the same features, but two different tasks. And the question whether the graph is good or not depends on the task, right? So we need to introduce some way of describing the task. And this was our work with also with Francesco, with Petter and other collaborators, where we try to characterize the task, which by task I mean a function that is computed on the graph and its features, through what we call mixing. So this is some kind of maximum on mixed second order derivatives. And you can think of some extreme cases, for example, when we have a fully separable function that has 0 mixed derivatives, So in this case, the mixing is 0, right? So there is no interaction whatsoever between the nodes. Or some other pathological cases where we have a nonlinear function that is applied to inner products of all the fishes. So in this case, all the nodes interact, right? And the amount of mixing depends on the nonlinearity of this function phi. So basically what we are trying to do with neural networks, right, you can think of it as we try to implement some graph functions in the form of message passing, right? And therefore, it's very important to understand how the architecture itself, right, like number of layers, the number of neurons and so on, the structure of the graph on which message passing happens interact with the mixing capacity of the functions, right, so of the neural network. So we want to write some capacity bounds that link all the things together, right? So the capacity of MPNN depends on the model and the topology of the graph, and the given task can be characterized through mixing. And that's the kind of the bound that we have here. So in red, we show some quantities that are derived from the adjacency metric of the graph, so they characterize the graph topology. And in green, you see constants that depend on the architecture, and in blue, you see characterization of the task through the mixing. So it's not maybe very informative, so it might be more informative to look at bounds, for example, on the weights or the depth of the architecture. And here we can lower bound the depths, so the number of layers that is necessary to achieve certain mixing, right? And it depends on both the structure of the graph, and we can come up with some impossibility results. So the depth here, you see it's proportional to what is called the commute time. Roughly, it's the connectivity of nodes by means of a random walker that can be as large as a polynomial in the number of nodes. So in practice, if we want order of 1 depth, it might be inachievable, right? And basically, we have a different way of talking about expressive power of graph neural networks without, again, resorting to the Weisfer element formalism. So we can state results of this kind of, right, maybe informally, that if I have a message passing architecture with L layers, it cannot learn tasks that require high mixing among features at nodes that are separated by a large commute time, right? And this also gives you a criterion that can guide graph rewiring, because you can, for example, try to change, to decrease the commute time, right? So to make somehow the nodes are accessible or more connected. You can also make it more granular, right? Because if you know the mixing of your task, then maybe you can adapt your architecture, right, or the graph structure for this particular class of functions rather than make it more generic. Now, there is one missing piece that we haven't covered, and I think I can finish in the next 5 minutes. So basically, when we talked about different flavors of graph neural networks, right, whether it's convolutional or attentional or general message passing, essentially we answered the question, what kind of information we're sending, right? So whether it's aggregated with a maximum or with a sum, or somehow nonlinear transformed information. When we talked about graph rewiring, we answered the question where to send this information, right? Whether I'm sending information only from my immediate neighbors, or maybe I'm looking at multiple hop neighbors, right? Or maybe I cut some edges. I don't want to consider information from some of the neighbors. But again, remember that this is a dynamic system, right? So that's the metaphor that I wanted you to have in mind. So the third remaining unanswered question is when to send this information, right? And this is also very important. So if you look at classical message passing, and let's say that I need to send information from the red node to the green node. So in classical MPNN, it will take 3 layers, right? Or 3 steps of message passing. So first information is sent to the neighbor, then from the neighbor to the neighbor of the neighbor, and then finally it reaches the green node. But on the way there, it is also entangled with other features, right? So as opposed to it in a transformer, which operates on a complete graph, the information from the red node will reach the green node in 1 step, right? Because we have edges between all the nodes. The problem, of course, that now the green node is flooded with information that might be totally irrelevant, right? So we can, of course, try to rely on attention to downweight this information, but sometimes it's, first of all, computationally expensive and might be inefficient. So what we try to do, we try to expand the receptive field, so we try to introduce this information gradually, right? And we can also do it through what we call geometric skip connections. So if we know that the information from the red node will reach the blue node, the green node, in 3 steps, we can create this skip connection between these nodes across 3 layers, and this information will reach the node exactly at the right time, but now it will reach it in a pure form without being mixed with the information of other nodes, right? So this is a kind of sparse skip connections. We call this dynamic rewiring. or Drew for short, and we've shown that these kind of architectures, so they act more generally than transformers. They actually outperform transformers on long-range interaction benchmarks, or at least used to outperform at the time when the paper was written last year. Now, another thing that we can do is, if you think of classical message passing schemes, right, whether with skip connections or without skip connections, basically every node has two functions. So it both receives information, so it aggregates messages from the neighbors, but it also sends its own information to its own neighbors in its turn, right? So it has both functions of receiver and transmitter. But we know that in some cases the node might be useful to send information only once, and then we don't need it to flood our computational graph, right, to flood the neighbors with this information, because it has already been accounted for and we don't need to repeat it anymore. So we want some more general message passing scheme where every node can decide whether it sends or receives information or it shuts up and doesn't do anything. So we call this cooperative message passing. So it's a form of asynchronous message passing. So Peter might have shown it in his talk in the beginning of the week. Basically, there are four functions that nodes can do in cooperative message passing. So it actually took us a lot of time to draw this picture with DALI. And if you think that we will be overwhelmed by AI in the nearest future, I think I still want LLMs to be able to do correct, even not matrix number multiplication. So I think we are still safe in this regard. So maybe these monkeys will jump out and kill us all. So anyway, but the node can broadcast and listen, right? So that's the standard message passing. It can only listen, right? Receive information. It can only broadcast, but not change its state, and it can isolate. So basically, the node acts independently. And this allows us to dynamically rewire the computational graph, right? So the node, there is a special mechanism. It's also implemented as a GNN that decides the action for every node. And we can show a bunch of nice properties. So it is more expressive than WL. It probably avoids oversmoothing. It probably avoids oversquashing. So again, what's the rub? So the rub here is that it is permutation equivariant only in expectation, because there is a stochastic part is sampling the action for every node. So if you're happy to live with approximate or equivariance and expectation, right? So in probabilistic result, then this is a very nice architecture. So I think I'm at time, so let me conclude. So I hope to have provided some new perspective on old problems in graph neural networks, if you're familiar with phenomena such as oversmoothing and bottlenecks, right? So we have this geometric perspective on them. We can also explain old architectures and hopefully also produce new ones by, for example, doing principled architectural choices such as residual connections, shared symmetric weights, as we've seen in the gradient flow framework. We can also provide theoretical guarantees, as again I've shown one result. I think it also gives nice links to other fields that are probably less explored in GNN literature and maybe ML broadly, like differential geometry, algebraic topology, PDEs, and so on. And we've also seen that the graph that is somehow considered sacrosanct in graph deep learning doesn't need to be such, so we can change it by means of rewiring, right? And we can also change it in a way that is dynamic, so we can also control not only what kind of information gets, where it gets, but also when it gets, right? So I think I will stop here. I don't know how much time do we have for questions, but thank you very much in the meantime.
Talk as always. We do have time for one question, and there is one question on the Slido, so I'm going to read that out. And Michael will be around for the breaks and lunch afterwards, so you can talk to him. We will only take one question now to make sure we have a good timing for the panel afterwards. So the question comes from Milos Vlajnic, and it reads, in your opinion, can graph neural networks be applied on precedence graphs, so item A precedes item B, for scheduling or planning problems on their own, or at least using them as a policy for reinforcement learning methods or something similar?
I think it has been done, well, I'm not sure, and I cannot cite necessarily a specific paper, but basically these type of graphs where you have head, tail, and some relation between them, right? And in this case, it will be precedence. So these are knowledge graphs, so graph neural networks or some form of graph learning have been applied to these type of problems, and there are now already foundation models for knowledge graph. So Michael Galkin, for example, so has an architecture that he calls Ultra, which is actually quite smart and very nice paper. So yeah, I suggest probably to look at this as a starting point.
Awesome. Let's thank Michael again.